So today we're going to introduce temperature related to kinetic energy, learn about thermal energy and heat, and talk about specific heat capacity. So the first thing is, what is heat? Well, the heat is the energy that gets transferred between two different objects at different temperatures. So temperature itself is just particles inside anything that is moving. So particles are always vibrating or moving, which means they have kinetic energy and potential energy. So temperature itself is the average kinetic energy of a particle, which helps us describe how hot or cold it is. Because if something is hot, the particles will move around faster. They'll have more kinetic energy, which means they'll have a higher temperature. If something is cold, it will move slower, it will have less kinetic energy, and therefore a lower temperature. So temperature, kinetic energy. Faster particles, more energy, higher temperature. Slower particles, less energy, less temperature. Okay, so we can measure temperature using thermometers, as you know. The symbol for temperature will be T, and the unit we will be using is Kelvin, sometimes Celsius. Fahrenheit is another unit, but we do not need to study Fahrenheit, so we can ignore this one over here. You can see that Celsius goes from 0 to 100 to boil, whereas in the Kelvin you have 273 to 373. The intervals are exactly the same. So, to convert between the two, we did a little investigation in class. You'll realize that whatever the Kelvin is, if you want to find it, you take your Celsius plus 273. For example, if you want to convert any of these, you'll just take whatever it is. For example, part A, 0 plus 273 is of course 273. 25 plus 273 is 298, and so on. If you want to go backwards, you can just simply subtract 273. So if I have Kelvin, you can subtract, and you'll get the answers in Celsius. 0K is the lowest possible temperature. We call it absolute zero. You cannot have anything less than 0. So if somebody says they got minus 10K, they clearly have made a mistake, because the Kelvin scale starts at 0. They will never be a negative Kelvin. Then we're moving over to thermal energy, which is the total energy inside. It's the kinetic and potential energy now. So it depends on the temperature and the mass, and of course the type of matter it is, water, oil, or whatnot. More temperature means more thermal energy, as we already know. More mass means more thermal energy, because there's a lot more particles available there, so that means there is more potential energy ready to be used. So we now know thermal energy is the total energy in something. More temperature and bigger mass would also mean more thermal energy. As mentioned before, heat is a transfer of this energy between two objects. Heat will always travel from hot to cold. Okay, heat goes from hot to cold. So something with a higher temperature will lose heat. Something with a lower temperature will gain the heat. Okay. This will keep happening until we reach something called thermal equilibrium. That means it is balanced. So if something was 0 degrees and 100 degrees, they will meet, and the energy eventually will be 50-50 in this case. It will be balanced. That's what we call equilibrium. So that is about thermal energy. As I mentioned, a different type of material has different energies as well. This is something we're going to talk about here called specific heat. Each different material has a different specific heat capacity, different amount of energy needed to raise the temperature. So simply put, specific heat is the amount of energy you would need to raise the temperature by 1 degree. Okay, there is a unit for it. We can call it joules per kilogram Kelvin or joules per kilogram Celsius. You can use either or. So, question then, what will heat faster? Something with a low heat capacity or something with a high heat capacity? You'll find something with a low capacity will heat faster, because if you had a high capacity, it will take longer to heat it up because it can handle more energy, more heat. So, specific heat capacity, amount of energy needed to increase the temperature of a 1 kilogram object, we're going to stick to 1 kilograms just to keep things fair, by 1 degree. Whether it's Celsius or Kelvin, 1 degree is 1 degree. More heat capacity, more energy needed. Okay, here is a little formula that we can use to find the heat using the heat capacity. The energy that you need, we will have to take whatever the capacity is and the mass. It might not be 1 kilogram, it might be more, it might be less. So the capacity times the mass times by the change in temperature that I am looking for. Maybe I want to increase it by 10 degrees or 12 degrees. That's what I will include into our formula. Out of here, which one will have a bigger specific heat? So in this example, we have 1 kilogram of gold, 1 kilogram of water. Which one has a greater specific heat? Well, you can see that the kilogram of gold goes from 20 to 90 degrees with this match, but the water barely increases at all. So, in this case, we can see that water has the bigger heat capacity because the change in temperature is less than it would have been with the gold that has more change of temperature. So, there's a quick example here. If I want to find the energy needed to take a 5 kilogram mass with a heat capacity of 4,000, and I want to have the temperature change between 8 and 12, how much energy would I need? So I can use my rule, EH equals, sometimes this could be Q, but we'll talk about that later. EH equals Cm change of temperature. So what I will do is I will take my C, which is 4,000, and then I'm going to do is I'm going to multiply that by the mass, and then I'm going to multiply that by the change in temperature, which will be final minus initial, 12 minus 8. So what I would do now is I'd simply just put that directly into my calculator to get the answer. So I'll do 4,000, I'm going to multiply it by 5, multiplied by 12 minus 8 in a little bracket, and I should get 80,000, 1, 2, 3, 4 joules. Amazing. Another example, if I had energy and I didn't know what the mass was, and I wanted to find the mass, well, I can do it. I can just rearrange the formula. I have my energy, E equals, I don't know why I wrote E differently, but it doesn't matter, Cm change of temperature. Of course, to rearrange this formula, that's supposed to be a T by the way, rearrange the formula, I want to keep M, so I'll divide both sides by C and the T. So I will do E over C and T, the change of temperature, equals M. So I've divided both sides. So now I can take this 8,000, 8, 1, 2, 3, divide that by 4,000, 1, 2, 3, multiplied by the temperature change. So it's told me the change of temperature. So I don't have a final or initial in this case. So to find this, I'll make a little fraction. 8,000 divided by 4,000 times by 40. My answer should have been 0.05 kilograms kg. Alright, so conservation of energy applies. So that means the total energy remains the same. So whatever energy the one gains, the other one would lose because it's being transferred. If I also write Q1 plus Q2, it should equal to 1, 2, 0. They will all add up to 0. No extra energy is created, no energy is destroyed. Okay, so rearranging that to the other side gives you this rule over here. Q1, Q2. Remember, Q can also be E, energy H. Sometimes it's written as Q, sometimes it's written as E for energy. It's the same thing, so don't worry about that. So that means I can have Cm delta T equals to Cm delta T for the other one. If there's more, you can add more of them, like Cm delta T all the way, and that should all add up to 0. So here is a quick example. You have a small ingot of metal, it's heated to this much, it's dropped into a calorimeter containing this much water at this temperature. The final temperature is this. Find the heat of the metal, the specific heat of the metal. No problem. So we have Cm delta T equals Cm delta T. They've just swapped the M and the C. Doesn't matter. It's the same thing. So the W would end up being the water. X is the metal that we're looking for. I'm trying to find C, so I will divide both sides by M and the T. So we'll divide both sides by M and the T, and now we'll get this rule over here. M, C, TF minus T, initial, divided by M, T minus TF, okay, which is rearranging this rule. I will take 0.4, this is my kilograms of my water, multiply that by the heat capacity of water. It is not here, it is given to you in the front page of an exam, and this is a constant, so there is the heat capacity of water, multiplied by the change of that temperature. It started at 20, and it finished at 22, so I'll do 22 minus 20. And then I will divide that by the mass of the ingot, and which is multiplied by the change of that temperature, 200 minus 22. And I will get 453 joules per kilogram Celsius. So that is done. There are 3 ways to transfer energy. You can have it through conduction, convection, and radiation. These are the 3 ways. Conduction is collisions. The particles get hot and they bump into each other and they spread the energy across them. So the particles are bumping in to each other, and this will be spread across solids, liquids, and gases. Because the particles of solids are closer together, it is more effective in a solid. It gets hotter faster. Convection is when the energy moves. The particles themselves start blowing around. The gases or the liquids down here in the liquid, they start moving. Hot air would rise, hot water would rise and cool down, and it will keep moving around. So this happens in fluids, which is a liquid or a gas, not in solids, because the particles are stuck in a solid. Radiation is the transfer of the energy through waves. Light, radio waves, gamma rays, X, all of these things. We're going to study this in more detail later. But all of these things transfer energy, and no matter is transferred. Just the energy itself is a wave of energy. Okay? Here's a little summary of everything that I've just discussed. Thank you.